everybody to this first Use a Chile workshop on hyperbolic geometry. This is, we hope, the first of many. This is organized by the Graduate Center and the Centro Geometry at the Frontier in UFRO, Temuco, Chile. So the idea is to start this collaboration with these two centers, and all this we hope that next year will be on presence in here in South part of Chile, so everyone is invited to come here next year. Hopefully everyone is okay with that. I don't know if Ara want to say something else also. Welcome.
Yes, I just want to say this is part of a bigger thing, and reiterate what Ruben said, that we intend to have actually events in Chile and events in CUNY at the CUNY Graduate Center, and hopefully go back and forth at least once or twice with both conferences and maybe visits from faculty and students. And hello, everybody, and it's a pleasure to be here. I'll hand it back to Ruben.
Okay, thank you, Ara. So our first speaker is Mary here. Thank you, Mary, for accepting to give this this talk.
Sure.
So yeah, so Mary will talk about big surfaces, mapping task group, and complex dynamics. Please, Mary.
Yeah, thanks. Thanks very much for the introduction and for the invitation. And special thanks to the organizers for this opportunity to bring us all together. So yeah, so today I'm going to talk about big surfaces, mapping class groups, big mapping class groups, and complex dynamics. So in particular, our surface will be the plane minus Cantor set, and we will see how this surface will arise very naturally in dynamics, and how the complex dynamics and the geometry and the analysis will interact each other. Okay, so let me just start with the most, basic object in mathematics. So that is polynomials. So in particular, we want to consider complex polynomials. Okay, so as we all know, so a polynomial is a map from the complex plane to itself. Right, and we want to consider polynomial up to some normalization. That is to say, so first we fix an integer d, which is greater than or equal to 2. This is the degree of the polynomial. And we want to consider monic and centered. So this is just a renormalization polynomials. So that is to say, the polynomials are of the form that it is monic, meaning the leading coefficient is 1. So the highest degree is z to the d, and centered means the roots of the polynomial add up to 0. That is to say, this polynomial does not have d minus 1 term. So you have a coefficient, which is d minus 2, so z to the power of d minus 2, and so on. And you have d minus 3 term, and all the way to z and a0. So where all the coefficients are complex numbers. And so of course, z is also the complex number. Right. So basically, complex dynamics is a branch of mathematics which basically studies what happens to every point on the complex plane if you iterate this polynomial. Say, like I take a point z in the complex plane and apply f of z and apply f to f of z. So I have this sequence z, f of z, and f of z, which I will denote by f square of z. So f to the power of n just denote composition. So complex dynamics started about 100 years ago, with Fatou and Julia, where basically they're examining points in a complex plane for sequences like this. So Fatou and Julia in 1920s. And what their contribution is, so this is what we call the Fatou set and Julia set nowadays. So Fatou, or the Fatou set, is the subset. Fatou set of F is the subset of the complex plane on which the sequence F squared, F cubed, and blah, blah, blah. So this guy, the sequence forms a normal family. Okay, and the Julia set is basically the boundary of the Fatou set. Okay, so there are other ways to express what the Julia set is, which is slightly more concrete. So I will define the Fielding Julia set. So this is more like modern term. Fielding Julia set is denoted by K of F. So this is the set of points in a complex plane such that these points do not go to infinity under iterations of the polynomial. So you take those points and you iterate your polynomial and observe where this point goes. So the Fielding Julia set for this polynomial is the set of points where those points do not go to infinity. So the Julia set, which is denoted by J of F, is the boundary of the Fielding Julia set. Or you can think of the Fielding Julia set is the complement of the Fatou set. So, but in this definition, it's very easy to see or get an idea of what is a Julia set, right? So the Julia set, so let's take the polynomial to be quadratic. So I just take this square. Then by this definition, the Fielding Julia set of z squared is basically the set of complex numbers such that these numbers do not go to infinity under squaring. So this is basically the complex numbers such that the modulus of the complex number is smaller than or equal to 1, right? And the Julia set in this case is, so this is the closed unit disk, and the Julia set is this boundary. So this is the circle. And in 2 minutes, I will show you more examples of Julia set. But now let me just continue a little bit to give you a few more definitions. So these are basically subsets of the complex plane associated to one particular polynomial. And in general, we want to consider the set or the space of all the polynomials. So this is monic centered. And this space is isomorphic to c to the power of d minus 1, right? So this is basically parameterized by the coefficient d minus 2, d minus 1, sorry, minus 3, 1, a0, and these are complex numbers. Right. So this is basically the space, the parameter space of all such polynomials. And in particular, we want to consider a subspace of this total space, because the total space is just c to the power of d minus 1, which is, you know, kind of simple topologically. And we want to consider something called the shift locus. So this is a subset of the parameter space. So this is defined as S sub D. So the shift locus in degree D is the set of monic centered degree D polynomial such that the field in Julia set contains no critical point of the polynomial. So F. So in other words, this just means, so the critical points are just zeros of the derivative of the map. So that is to say the critical point will all go to infinity under iterations of the polynomial. So let's, again, to get an idea, let's look at what happens for degree 2 polynomials. So we have P of Z. So the degree is 2, so we have Z squared plus, since it's centered, so there's no Z term. So A0, right? So where A0 is a complex number. So the total space of quadratic polynomials is the complex point, right? So it's parameterized by this C. And what is the shift locus in degree 2? So by definition, we need to look at what is the critical point doing, right? So the critical point of this polynomial is the 0 of the derivative. So that is to say, 0 is the critical point. So in this case, we only have one critical point, and there's a dichotomy, right? So either this 0 will go to infinity, P of n will go to infinity, or it will not, right? So you iterate and observe what is the orbit of this point 0. So it's either go to infinity or not. So this dichotomy gives the definition of a subset of the complex plane, the parameter space, which is the famous Mandelbrot set. So basically the Mandelbrot set is the set of parameters, so A0 inside C, such that basically this is the case where the orbit of 0 does not go to infinity. And again, so by definition, the shift locus is the set of parameters such that the critical points all go to infinity, right? So the critical point is 0, so 0 goes to infinity. And you can see this is basically the complement of the Mandelbrot set. So this is C minus the Mandelbrot set. Okay, so let me try to do this. Okay, so yeah, let me try to share this program with you. So the picture on the left-hand side is the Mandelbrot set. So this black guy, and the picture on the right-hand side is the corresponding Julia set. So now you can see the yellow dot, cross is at the point where the complex parameter equals 0. So this point represents the polynomial Z squared, and you can see the Julia set is the circle. So the green part on the right-hand side is the Fatou set, and the black part is the fielding Julia set. So its boundary is the Julia set. And if I move, you can see the Julia set changes and it becomes very fractal. So if I move here, so you can see this is basically the basilica. And if I keep moving, then you can see very, so this is Duarte rabbit. And I think this is like a cocoa pellet. And this is the dihydrate. Okay, so you can, and so this is the Mandelbrot set. And if I move outside of the Mandelbrot set, so you can see from here, the Julia set is a Cantor set, right? And so this is very important. So if I move my parameter outside the Mandelbrot set, you can see the Joule set is changing. And as long as I am in the shift locus, which is the complement of the Mandelbrot set, the Joule set is a Cantor set. And here is a Cantor set. This is also a Cantor set. And you can see this Cantor set dancing around. So what is cool, if you look at the right-hand side, the Joule set is a Cantor set. What about the green part? The green part is the plane minus a Cantor set, which is our big surface. So this is where the big surface comes into the game. So basically we want to, in order to study the shift locus, the space of these polynomials, we can look at this big surface, which comes from their dynamics. And we can look at this collection of big surfaces for all polynomials outside of the Mandelbrot set. And we will develop a combinatorial model for the space of these big surfaces, which is also the space of shift locus. Okay, so let me stop here. Yeah, let's come back. So as we saw on the picture, so if we take a polynomial, which is in the shift locus, so the dynamics is very nice. So first, the Joule set of the polynomial is a Cantor set. So the field in Joule set is also the Cantor set, right? So that is to say the Fatou set is the plane minus Cantor set. And this plane minus Cantor set is not just topologically a plane minus Cantor set. It is equipped with this dynamics, this polynomial dynamics, and also because SIG is complex, it's actually a Riemann surface. So we will see how these analytic and dynamical and topological features of this big surface come into play. And also, the dynamics is uniformly hyperbolic. So the map is uniformly expanding on a neighborhood of Joule set. So this dynamical system is hyperbolic. And more precisely, this dynamics is, so the dynamics of the polynomial restricted to the Joule set is conjugate to the shift. So this is why this subspace is called the shift locus, because the dynamics is basically just shift. So this is the one-sided full shift on the layers. Okay, so I will draw you a picture for the case when d equals 2. So basically, like, suppose this is a neighborhood of the Joule set, and your surface or your marker partition for experts will look like something like this. And for each circle, you will have a figure 8, right? And you can imagine like the Joule set is sitting in the limit, right? So the Joule set is a Cantor set. Okay, so we will see this picture again. And what we want to develop is something that we call the Butcher paper. Out of this Riemann surface. And this is a combinatorial model for the shift locus. Okay, so how does this construction work? So it starts from a very old theorem by Butcher, which says the following. So if F is a degree D monic and centered polynomial, then there exists a holomorphic isomorphism phi sub f from a neighborhood of infinity of f to a neighborhood of infinity, conjugating this polynomial to the standard map, which is just z goes to z to the d. So that is to say, near infinity, all the polynomials look the same. So they just look like z goes to z to the d. So let me just draw you a picture. So near infinity, so this is the dynamics for f, so near infinity, and this is the butcher map. And this is, I'll draw a standard circle. So this is a neighborhood infinity corresponding to z goes to z to the d. So our goal is to construct a Riemann surface such that this Riemann surface is conjugate. So we'll eventually construct this Riemann surface equipped with the dynamics z goes to z to the d, which is conjugate dynamically to the polynomial we started with. Okay, so here is how the construction goes. So from the butcher map, so I can consider the following. So on this side, this is a neighborhood infinity, or you can think of it's like vertical cylinder where infinity is on the top, right? And here I can consider foliations, like ray foliations, right? And what I can do is I can I start with this ray foliation, and I can pull back this ray foliation. And what I get on my dynamical plane, so this is, again, this is infinity, and this is the dynamics for f. Right? So what I get is I can consider this as a vertical cylinder. So I get an analytic foliation until I hit the first critical point. So basically, what is a critical point, right? If you remember the degree 2 picture, so this is a critical point, right? Because z squared would be a double cover of, so you can think of this circle is a branch cover of the figure 8, branch at the points when you see a cross, right? So this is the critical point, and the smaller crosses are the pre-images of the critical point. So if I draw them like vertically, right, it looks like something like this, and it looks something like that. So this, if you can see, this is exactly the counterpart surface, right? So what does the foliation look like? So it comes from infinity, so it looks like vertical lines. So it is an analytic until I hit this point. So this leaf, so there's one at the back, this leaf will stop being analytic once it hits the critical point, right? And these ones will continue because they're analytic. And they can analytically continue these guys. So just analytically continue. And again, this guy will stop being analytic until it hits this pre-image of the critical point. So I will basically get a foliation which looks like this. And if this guy is lucky, it never hits any critical points. It goes all the way down to the Julia set, to the Cantor set, right? So in this way, I get, in the end, after I analytically continue this pullback foliation, I get a singular foliation. So on this, on the Fatou set of f, right? And so now I can construct what we call the butcher paper. So remember, this is the tool set for F, and we can go back. So this is the butcher map. So the butcher map is defined only on the neighborhood infinity. So now I can use this. So it's originally defined here, and to the infinity of z to the d. So now I can use this singular foliation to extend this butcher map, right? So I just follow the leaves of the foliation, and then we'll encounter problems if I hit the critical point. So that's exactly the information we want to record. So, so how should I do this? Let me change the color. Again, so this is basically like where this map is originally defined. And I just follow these leaves, right? So on this side, I can think of everything is, so this is the unit disk. And I can think of E to be the complement of the open unit disk, right? And infinity is very far from there. So I will see basically rays coming into that. So based on this foliation, so on this on the right-hand side, this picture looks like something like that. But this foliation will stop, right? Because here, after this point, so these pent seams is really not part of the foliation. So that is to say, so for some ray that comes in here and it will stop here, right? And also there's a ray which is at the back of the surface, the back of the pants. So this guy will come like this way. And again, because it hits the critical point, it will stop here, right? And so if you do this again, so for the pre-image of the critical point, it's somewhere here. So this ray will go longer because it's deeper, right? And at some point it will stop. And since there's another one at the back, so I think this one is here, right? So basically what we want are these dots. So these dots, the black dots, are what we call the cut points. And so let me just draw the picture again. So you have this complement of the unit disk, and you have these dots. And what you want to do is you connect them up to the boundary of the unit disk. Okay. And what does this mean? So this just means, so I will connect these guys up to mean now I will just, if I start with this piece of paper and it will cut along these black lines, and now I will also cut along here. And if they are connected, it means, so if I cut along, the black will become two guys, right? It means these two guys will get glued together. So this guy is glued to here, and this guy is glued to here. And as you can imagine, this gives you, so this longest black guy topologically gives you this same, right? So if you cut along, you get basically kind of like a pair of pants. And then you cut along the smaller, the shorter guys, you get a shorter pair of pants. So you get something like here. And you can do, so you basically just get, so these are the pre-images of this. And you keep doing, so this is in degree 2, how it looks like. So you basically just keep doing. So every point has 2 pre-images. And so this guy is glued to here. It means you cut along these 2 guys and glue them together. So this is how you can build, so this cut and glue will give you a Riemann surface. which I denote by omega. So omega is topologically also plane minus Cantor set, right? It's basically a Cantor pants, and it's equipped with the dynamics z to the z to the d. And moreover, so the point is the factorial set of f with the dynamics f is conjugate to this Riemann surface I built by this Butcher map, so, or this extended Butcher map. And this extended Butcher map is which is a holomorphic isomorphism. So they are isomorphic as Riemann surfaces. Okay, so this is just one side of the story. So far, we start with the map F in the shift locus, right? And we can construct this Butcher paper, this Riemann surface. Or this is what we call the Butcher paper. And as I said, we want to build a combinatorial model for the shift locus. That is to say, we also kind of want to build as a space, they're isomorphic, right? So we will also want to go backwards. That is to say, I want to start with an abstract Butcher paper, and I want to show there exists a unique polynomial in the shift locus which realizes this Butcher paper. So let me start with the definition of formal Butcher paper or formal shift map or something. Okay. So yeah, so basically we start again with the set E, which is the complement of the unit disk, and this is equipped with the map z equals to z to the d. And how do we construct this Butcher paper? Well, remember, the only information we need is really basically the critical point, right? So these guys, because you can get the smaller guys by taking square root or dth root of this guy. So if you take square root, you get two guys like this, right? So if, I don't know, if this is 2, then you take square root 2, so you get something like that. And so once you know, so the point is, once you know the information for critical point, you can basically recover the rest. So those are just like self-similar image of this critical point. Okay, so basically the data is the following. So first you take an unordered set V inside this E to be, of D minus 1 points to be the formal critical value. And number 2 is for each critical value. So you will have, generically, you will have the pre-images, but you could have multiplicity. So for each critical value of multiplicity k, so you find an unordered subset consisting of k plus 1 of the D pre-images of V. So generically in degree 2, so the picture just looks like this. So you have one critical point, and every guy has 2 pre-images. So these are formal critical points, and they should satisfy something called unlink. So this is satisfying the unlink property. So this is required for higher degree polynomials where you have more than one critical point. So this property says no formal critical point may link each other. So yeah, I will just draw you a picture. So this is again the complement of the disk. So now suppose I have two critical points. So I will have a red stick. So this means they're connected. Again, you can cut along these two reds and glue them together. So this looks like a pair of pants, right? And I can also have another critical point, something like this. And again, if I cut them up, then this is a shorter pair of pants. So the unlink property just means these guys. So these red and blue inside the disk, which suggests which one is glued to which one. So these guys are not linked. In other words, if you draw the complete pre-images, they form a lamination of the disk. Okay, anyway, so this is basically the information we need to construct a formal butcher paper or formal shift map. And our theorem, so this is the realization theorem. So yeah, the realization theorem basically says there exists a unique polynomial in the shift locus whose dynamics is holomorphically isomorphic to this butcher paper with the map z to the z to the d. And this realization theorem is essentially, I mean, erase. So it's essentially due to Laura DeMarco and Kurt McMullen. In a different kind of model for the shift locus, but let me just write Juliet, Danny, myself, Sarah, and Olin. Okay, cool. So this is basically, yeah, the idea is basically the same, but the details are kind of a little bit different because we're dealing with two different models. So the realization theorem says, just as I said, there exists a unique polynomial in the shift locus for which the action of f on this plane minus Cantor set is conjugate to the action of big F, which, sorry, this is C goes to Z to the D on omega, and it is conjugated by the butcher map. Okay, so that is to say the space of polynomials in the shift locus, so or simply the shift locus, is holomorphically isomorphic to the space of butcher papers. And this is just omega and Z goes to Z to the D. Okay, so this is the story about big surfaces. So now I'm gonna tell you how mapping class groups comes in. So let me just go back to my computer. Again, we can come back to the picture of the Mandelbrot set, right? So the Julia set, so if I pick a point here, Yes, so the van der Waals set is small. Yeah, I hope people can see the right-hand side. Yeah, so if I pick a parameter here, right? So this is a Cantor set, and this Cantor set is contained in the real line. So it's just like a middle third Cantor set. And if I start moving the parameter, then you can see the Cantor set will also start moving, right? And if I just move like this, then you will see like the Cantor set started to tilt, and you can imagine what I can get if I just loop around the van der Waals set. And you can see the Cantor set just keeps kind of like rotating, right? And here you will get a cauliflower. And then the cauliflower will just rotate again, and it will come back. If I come back to the starting point, so it will be again a Cantor set which is contained in the real line. So you can think of this shift locus or the whole picture as, so for every point in the shift locus, the Joula set is a Cantor set bundle. So you can think of this whole thing as a Cantor set bundle over the shift locus. So if I loop around, I take a loop in the shift locus, then when I come back to where I started, I should get an homeomorphism of the Cantor set, right? And in particular, since the dynamics is hyperbolic, so it's also hyperbolic in a neighborhood of the Joula set, so I can extend this homeomorphism to be a homeomorphism of the plane minus the Cantor set. So because like the neighborhood of the Cantor set also moves the same way as how the Cantor set is moving. So again, if I do this, so you can see if I go along a loop, I should, when I come back, I should get a homeomorphism of the plane minus the Cantor set. So this is how we can also get the relationship between the parameter space in complex dynamics and the big mapping class group. So let me just stop share and let's go back. So let me just, sorry. Yeah, let me just write down what I just said. So basically what we get is a map. So this is from the fundamental group of the shift locus, right? Because I take a loop, and this is a map from the fundamental group of the shift locus into the mapping class group of this plane. Topologically, it's just R2 minus the Cantor set. And in particular, so if I take gamma, the image under this, maybe let me just call this big phi. So the image under this monodromy map, so this is the monodromy map. So this guy is a mapping class. And in particular, this mapping class commutes with the dynamics. So this mapping class commutes with the dynamics at gamma 0, the base point. Okay, so there are a bunch of things we want to understand for this map. So the easiest case is when D equals 2, right? So this is the picture we just saw. And this is because the space S2 is particularly simple. So there are many ways to say this. So topologically, this is S2 has homotopy type S1. So this is just a circle topologically. And how do you see this? So this is, remember, this is the van der Waals set and something like that, the black stuff. And the green is the shift locus, like in our picture, right? So this, there are many ways. So So this is, the theorem says the Mandelbrot set is connected. You can see this using the Butcher space. You can see for when D equals 2, you only have two sticks, right? And topologically, this parameter space is the annulus. So this is a circle, and its complement, which is the Mandelbrot set, is connected. And this theorem is also proved by Duarte and Hubbard, or you just say by Duarte and Hubbard, this is connected, so the complement is a circle. Anyway, so this basically says in degree 2, the shift locus is very easy to understand. So this is just a circle. And we also understand what the mapping class is. So the mapping class is basically braid. So let me quickly just draw, as I'm running out of time, what the mapping class does. So this is my Cantor set, right? So it has two chunks in particular. So let me just draw it better. So because it's quadratic, right? The Markov partition, every guy will have two sets and you have that. So the mapping class is an infinite braid. So if you think about these guys being 4 points, then it's basically just braid group on 4 strands. But you have a Cantor set worth of points. So this is a little bit hard to imagine. How does this go? So since you have a coding for this, right? So if I denote left by 0, right by 1, so this part is 0, 0, and this is 0, 1, and this is 1, 0, and 1, 1. And every part has a calling. So basically the mapping class will be such that it swaps 1 and 0. So in the end, it will look like something like that. But it's not that simple because the Cantor set is self-similar. So the mapping class is also self-similar. Well, because it respects the dynamics, right? So that is to say, you look at this strand, it further splits into 2 strands, and every guy, so let me just draw this. So this strand is actually 2 strands in a self-similar way. So it's like, it's like this, and like this, and again, this guy is actually like 2 strands. Like you need to work a little bit to figure out which one is in front of which. So you can think of this like splits further and further, and it's a self-similar infinite braid. So this is basically the mapping class we get for degree 2. So when degree D is greater than or equal to 3, the shift locus is very complicated. So because you have more than one critical point, and the behavior of the critical points are more complicated than degree 2. And I think this is almost a theorem where we prove that this map, when D equals 3 into the mapping class group of the plane minus the Cantor set. So this monodromy map in degree 3 is injective. And in general, we think it's injective, but for higher degree, it's very, very hard to compute, or the combinatorics for the shift locus is very complicated. Okay, so I'm running out of time, but let me just say a few words about the proof. So it's after lunchtime, but let me just say the proof uses sausages and butcher papers. So I don't know how many people are interested, but if you are interested, I can tell you where to go. So you can find on archive. So this is 11265. Okay, so I will stop here and thank you for your attention.
Thank you, Marie. Let's thank her. So if we have time for some questions, so open your microphone and you can ask.
I have a question. Mary,
Oh, yes.
can you just give us a quick idea of what a sausage is?
Okay. So that's an excellent question. So it's algebra geometric. So actually, okay, so I can share my screen. If I stop sharing here, stop sharing here. Yeah, sausages and butcher paper. So here, the interesting thing is here it says Julia Bavard's sausage supplies. Okay, so yeah, so basically it's algebra geometric construction of the cells of the butcher paper. But I want to show you what the sausage is intuitively by showing you this amazing picture. So the basic idea of how to making sausages is the following. So basically, this is how we make sausages. Yeah, I guess the idea is you make the sausages piece by piece. So it's like you topologically you construct a cell and you glue another cell together. But the tacking point is basically like where you have a degenerate critical point. So you have like two critical points when they collide, you have a singularity in your algebraic variety, right? So basically like the parameter space will somehow look like this. So you have basically a piece of cell, and then you just glue another cell at the corner point. Then you just make another sausage. Like that. Does that answer your question?
Maybe. I'm not really sure. Is that a finite process? The gluing process you're talking about?
I think it's infinite, but it's self-similar. So you only need finite data. So after which you just iterate backwards, kind of.
Okay.
Yeah.
I had a question.
Yeah.
Thanks for the talk, by the way. It's about the topology of the image of the monodromy. Do you know if this is always discrete, or does it accumulate somewhere?
I think it's discrete. Because if it's an injective, right, then the fundamental group of the shift locus is countably infinitely generated. Then yeah, it is discrete.
Okay.
So is there any other question around that? So if not, let's thanks again, Mary.